Hello everyone, my name is YongbinCho and my project is about DTMF, signal generation and decoding. DTMF means dual tone multi-frequency, and this one is usually used in telephone dials tone. And we'll try to decode the telephone number by FF using FFT to telephone dial sound. So what is exactly DTMF? DTMF stands for dual tone multi-frequency, as I told, and it's the signaling system used in virtually all push-button telephones. The key idea is each button on the keypad produces a unique sound by adding together two sine waves at different frequencies. If you look at the table on the right, you'll see how this works. The keypad is organized as a 4x3 grid. Each row is assigned to frequency 697, 770, 852, or 941 Hertz. And each column is assigned to a separate frequency, 1209, 1336, or 1477 Hertz. When you press a key, a phone generates the sum of its row frequency and its column frequency. For example, pressing the digit 5 produces a tone that is sum of 770 Hertz and 1336 Hertz. Mathematically, this x of t equals sine of pi 2 times 770 times t plus sine of 2 pi times 1336 times t. Now we'll start with problem 1, signal generation of DTMF. So I'll just select a random phone number, which is 0423501 234, and uh, for for each digit, we look up its row and column frequency from DTMF table and generate 0.3 second tone by summing two sinusoids. Between each tone, we insert 0.1 second silence. Our sampling frequency is 8000 Hz, which is more than sufficient for the highest DTMF frequency, which is 1477 Hz. At this rate, each tone consists of 2400 samples and each silence is 800 samples. For a 10-digit number, the tone signal length is 32,000 samples, or exactly 4 seconds. So we look at the so you can hear the sound wave that DTMF makes. And in part 2, we now conduct entire FFT to the entire signal. Looking at the magnitude of spectrum from 0 to 2000 Hertz, we can see peaks at all 7 DTMF frequencies, and they're all clearly visible. But we cannot actually find out which phone number is it because all the signals are present in the FFT signal, and we don't know what number someone pressed after FFT. So now we will do FFT after segmenting the signal. We divide it into individual segments one for each digit, and compute the FFT of each segment separately. Each 0.3 second segment contains exactly one digit dual tone signal. When you compute its FFT, exactly two prominent peaks appear in the spectrum, one from low frequency group and one from the column frequency group. So after that, we use MATLAB find peak function to automatically locate the two largest peaks in each segment spectrum. Then you compute the detected frequency to known DTMF frequency table to determine which key was pressed. So after verifying the conducting, you can see that can find the which digit is the number, and we can finally find the entire phone number which is pressed, and it's correct. After that, I tried to add Gaussian noise to the signal at various SNR levels from 20 decibel to all the way down to negative 10 decibel, and repeated the decoding process from part C 50 times to see the success rate of FFT. And the result is that 100% of the FFT, even though there was Gaussian noise, was successful. So if you see the result, you can see that the success rate is all 100%, even though there was noise added to the original signal. And that the success rate is 100%. And this is the reason why is the noise, the energy of the noise so the peak of the noise is more significantly larger than the SNR noise. And this is the reason why FFT result is not didn't change even though the noise was added to the signal. After that, I try to look at aliasing by changing the sampling rate from 8,000 hertz to 2,500 hertz. And if you look at the result, until 300 hertz, the result was almost correct. The decoding result was correct, but under 3,000 hertz, the aliasing occurred and you weren't able to find correct phone number. So if you look at the result, as sampling rate goes down to 3,000 hertz, the result of phone number decoded was wrong. And if you look at the graph, so you can see that the peak moved from 1,477 hertz to somewhere lower. So the result was different. Aliasing occurred and affected the result. So, and then I tried to how to choose a window function that affects FFT spectrum of DTMF signal. In lecture, we learned that applying the FFT to finite length signal is equivalent to multiplying it by rectangular window, which introduces spectral leakage, energy spreading from the true frequency into neighboring pins through side lobes. We compare three windows applied to first digit segment. The rectangular window, meaning no windowing at all, has the narrowest main lobe, giving the sharpest peaks, but side lobes are only 13 decibel below the main lobe, which is relatively high. The Hanning window reduces side lobes to about negative 31 decibel at cost of slightly wider main lobe, And the Hamming window pushes side lobes down to negative 43 decibel, the lowest of the three. Looking at the spectral plots side by side, the difference is visually obvious. The rectangular window shows noticeable leakage spreading around the peaks, while the Hamming window produces much cleaner, more isolated peaks. Now, in terms of decoding accuracy, all three windows achieve 100% success, which is consistent with what we learned from Part D about FFT's robustness. The DTMF peaks are so dominant that so the noise was not large enough to affect the FFT result. But if the noise is big enough, then this result may affect the final result. After that, I tried to conduct STFT spectrogram visualization. And so STFT is short-time Fourier transform. And as a result, we can see that the yellow lines are the peaks of each signal, and the green line is other parts, and the darker side is the gap between signals. So by making this spectrogram, we can maybe use convolutional neural network or others to analyze the signal visually. And the concepts I used is as follow in the lecture. Thank you for listening. And this is the end.